All right, now welcome to this. All right, now what I said before is this because I didn't show the screen before. All right, now what is a bond angle? What do we mean by a bond angle? Well, an angle in maths, as I say, is like this, isn't it? You need 3 points, A, B, and C, and there's the angle between A, B, and C, the 3 points. Okay, and in maths we would say A, B, C, and we put a little angly thing over the top, and there would be a bond angle. Angle in this case is theta. All right, so the point I'm trying to make, you need 3 points are needed. 3 points needed to define a bond angle. Okay, 1 point, 2 points, 3 points. If you've only got 2 points, B, C, if you've got a line, BC, there's no defined angle here. There's no defined bond angle. Okay, there's no angle there, is there, between B and C? Now, the point, oh, and that sounds like someone's putting their hand up. Yeah, Natalie, oh, she wants to come in. Is she outside Maripola? Okay, there you go. So, where are we? So, if you've only got 2 points, you can't define a bond angle, can you? If you've only got 2 points on a line, there's no there's no angle defined there. So it's the same with diatomic molecules. So if we look at diatomic molecules, okay, like HH and HCl, for example, there's only two atoms, so there's no defined bond angle here. No defined angle. So for diatomic molecules, all right, there's no defined angle, and so we don't have bond angles for diatomics. There are no bond angles. No bond angles for diatomics. All right. So you need, and the whole point of the reason I'm saying all this rubbish is you need 3 atoms to define a bond angle. Okay, like in maths, you need 3 points to define an angle. In chemistry, you need 3 atoms to define an angle. So let's have a look at a molecule here. Let's have a look at ethanol. Okay, and let's have a look at this angle here. Let's call this angle A, this angle B, and this angle C. So in chemistry, we'd say angle A, is the HCH angle. We put an angle sign here. What does that equal? Well, in this case, it's 109.5. Angle B, we'd say this angle B this is A, by the way. Angle B would be HCO. Okay, and we put a little angle thing there, and that one would also be 109.5. And then angle C would be defined as, this is B, angle C would be angle between C, O, and H, and that I think is 104. Does that make sense? Are we all clear on what I'm trying to get at there? Yes or no? Are we all good? Okay, do we understand that? Type in the comments if you understand what I'm talking about there. Does that make sense? Anyone? 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 Can anyone hear me? Are your computers not working today? All right, can you not type? Just type in, yeah, I understand, or level hang's good. What about Madvika? Do you understand? Madvika's good. What about Natalie? Oh, I think Natalie, are you there? Natalie. Oh, I don't think Natalie's there anymore. All right, so there you go. So that's what we mean by bond angle. You need 3 points to define the angle. All right, we've done that. Okay, I thought this would be an easy lesson, but I'm wrong. All right, so we use the valence. I can't remember what this is called exactly. Valence shell. Oops, that's a double L. Electron pair repulsion theory. This is what we use, okay? VSEPR. We use this theory to tell us about bond angles. Okay, now the VESPA, this thing, basically all it says is electrons repel each other. Okay, and in repelling each other, they try to get as far away from each other as possible. They try and get as far away from each other as possible. That's all it means. So let's imagine a sphere. Here's a sphere, and this is our central atom. Okay, so electrons on the central atom, if you've got 2 electrons on this side and 2 electrons on this side, okay, they'll maximize their separation. So these guys will maximize separation. And if they maximize separation, they minimize repulsion. Okay, so how do they maximize separation? They get as far apart as they can from each other. So these, if you've only got 2 pairs of electrons, they'll get to either side of the sphere, and the bond angle between these 2 will be 180 degrees. That's all we're trying to say here. All right. Now, in future, I'll call this an electron direction. And I'll call this an electron direction as well. So we'll say in this case, we have 2 electron directions. Okay, and if you have 2 electron directions, the bond angle, well, they'll get as far as they can from each other. Bond angle will equal 180 degrees. All right, and we call such bond angles linear. Okay. So that's a linear one. All right, now I think the best thing to do is look at examples because that's where we really understand what's going on. Okay, so let's have a look at example number 1. So 2 electron directions. We've talked about this just now. And the common example here is, oh dear, someone's calling again. All right, Natasha wants to come in again. Natasha, oh, hold on. Oops, I think I pushed the wrong one. I think she better call back in a minute. I think I've just denied her entry. I'm using a pen, not my mouse, I'm afraid. All right, 2 electron directions. And the common one used for this is carbon dioxide. Okay, so let's draw carbon dioxide. This is carbon dioxide. And what would carbon dioxide look like if we were to draw the dot and cross or the Lewis structure? It would be a carbon there, an oxygen there, an oxygen there, and you'd have 1, 2, 3, 4, 1, 2, 3, 4, 4 electrons between the carbon and the oxygen, and 4 electrons between the other carbon and the oxygen. And there you go. That's the Lewis structure or the dot and cross of carbon dioxide, isn't it? This is the Lewis structure. Whoops, I just saw a structure. Okay, now how many electron directions are around the central atom? Now, obviously, we want the oxygen, carbon, oxygen bond angle. This is the one we want. Okay, that one there. All right, so the bond angle we're looking for is this one. What is that bond angle? Right, first of all, we look at how many electron directions are. There's 1 electron direction around the center one. We always look at the central atom. We're looking at this one to see how many electrons directions there are around the central atom. There's the other one. So this one obviously has 2 electron directions. So these will minimize repulsion by getting as far as they can across. They'll minimize repulsion by getting as far apart as they can over the carbon, the central carbon. So there will be this kind of shape. So this one is 2 electron directions, so they'll form a bond angle. In this case, the bond angle will be 180 degrees. Okay, and carbon dioxide is a linear molecule. okay, with a bond angle of 180. Are there any other linears? Well, the one in your course I can think of is the nitrile. All right, let's have a look at this compound, hydrogen cyanide. This is hydrogen cyanide. If we were to draw hydrogen cyanide, we'd come up with this, wouldn't we? We'd come up with a central carbon. We'd have 6 electrons here, 1, 2, 3, 4, 5, 6. Nitrogen there, and we'd have 2 electrons here, hydrogen here, and there'll also be 2 electrons there. All right, how many electron directions are here? Well, again, we look at the central atom. There's 1 electron directions for these 2, and this is a second electron direction. There's 2 electron directions. There's 2 bunches of electrons. So this would be linear as well. So if I looked at the HCN, this bond angle here is also 180. Okay, so this is linear as well. Okay, so you can tell if you can draw the dot and cross diagram to find the electron directions, or you can draw the structural formula. Okay, if you use the dot and cross diagram, you can see there's 1 electron direction, 2 electron directions. If you use the structural formula, you can see 1 and 2. So if there's 2 electron directions, it's going to be linear. Okay. All right, and that's it. That's 2 electron directions. And the example often given is carbon dioxide. All right, let's have a look at 3 electron directions. Okay, now this is 3 electron directions. Okay, now the common one here is given as boron trifluoride. Okay, BF3. All right. Now, if we were to draw boron trifluoride, it would look like this: B, and you'd have 1, 2, 3, and over here we'd have F, F, and F, and we'd have our. There you go, our fluorine electrons there. All right, and it would look like that. Okay, so this is 3 electron directions. Now, what are 3 electron directions around what? Around the central atom. Okay. Oh, I think someone made a noise there. Let's have a look. Is someone knocking on the door? Oh, she still wants to come in. I've let her in this time. Last time I don't think I did. Natalie, are you there? Is anyone there? I don't. You keep cutting out or something. What are you doing? Are you on a phone? Phones aren't very good for these sort of things. You really need a laptop for these. Anyway, all right. You what? Sorry, I can't hear you. Oh, no one can hear. All right. Anyway, so we've got a central atom there, and as you can see, the boron is there. So now, if you imagine you've got a central. This is the boron. All right, nice sphere. Okay, whoops, we don't want that, do we? And we want the electrons arranged. How the electrons are going to be arranged around the boron? Well, they're going to get as far apart from each other as possible. Okay, so they're going to do this kind of shape. Now, looking at this is the top view. We're looking from the top view here, and we're looking at this angle here, and this angle is going to be 120. Okay, from the top. Now, interestingly, that's the biggest angle you can get on a sphere with 3 electron directions. If you looked at this from the side view, okay, and now here's my sphere again. Okay, this is my boron. All right, you would have, this is a side view now. You'd have electrons. This is at behind now. And you'd have electrons here. So the side view, even though it's hard to see from my awful diagram, is going to be flat. Oh, what's that going on there? So the side view will be flat. Okay, so from the top view, it looks like this thing with the bond angle of 120, but from the side view, it's flat. And things that are flat in chemistry, we call planar. So the boron trifluoride molecule is planar. It's flat. Okay, so let's have a look then. What shape will it be? Well, it would look very simply like this. All right. with this angle 120, and it's flat. And this is called trigonal planar. It's a trigonal planar shaped molecule. So if you have 3 electron directions, you get what shape? You get trigonal planar shaped. Okay, any 3 electrons. Any 3 bond directions. And there's 1, 2, and 3. 3 electron directions, and it's going to be trigonal planar. It's going to be flat. Where else do we see this? Well, we see this in the carboxylic group. Let's have a look at ethanoic acid. There's ethanoic acid. All right. Now, where is it? Well, look at this carbon here. Okay, it's got 3 electron directions. So this part of the molecule must be planar, and it must be trigonal planar. This part of the molecule is not planar. This is not planar. And this part is not planar as well. Okay, but this part with 3 electron directions around the central carbon is planar. So if someone asked you here what are the bond angles here, first of all you would have to define which bond angle I meant. Let's define this bond angle. This bond angle is OCO. That's going to be 120. This CCO is going to be 120, and this CCO, the top CCO, is also going to be 120. So there you go. They're all, and if it's got 3 electron directions, it must be trigonal planar. Okay, so we're done with that. All right, so let's get rid of these. All right, now let's do the hardest one, 4 electron directions. This is the trickiest one. 4 electron, not electrons, electron directions. Now this one is the one that we find the most tricky because there are 3 types, but they are all based on a tetrahedral. They're all based on a tetrahedral. So if you have 4 electron directions, it must be based on a tetrahedral. Okay, so let's separate my my page here into 3. So let's put a line here and a line here. Okay, and let's do the 3 types. Right, so the first one we're going to look at is methane. That's the most common one for this. The next one is ammonia. And the last one is water. Okay, so let's have a look at a methane molecule. Methane molecule looks like this. Okay, and it's got a bond there, it's got a bond there, bond there and a bond there. Ammonia, what does ammonia look like? It looks like this. It's got, oops, let's do this color. It's got a bond there, 2 electrons, 2 electrons, 2 electrons. And interestingly, ammonia has also got a lone pair. So it's still 4 electron directions because of the lone pair. Now, and what's water look like? Water is gonna, let's do water in blue. Water is going to be a central oxygen, a hydrogen here, and a hydrogen here. Where are the electrons? 2 electrons there, 2 electrons there. But oxygen has 2 lone pairs of electrons, so it still has 4 electron directions. So all of these shapes are all based on tetrahedra. That's very important. So let's draw a tetrahedra. How do we draw a tetrahedra in chemistry? We do this, the central carbon, central nitrogen, and central oxygen. Okay, so we have a bond up here. This is how we draw a tetrahedral, which I'm sure you know. Now, there you go. This one is a wedge, and this one is dotted line. That's how we draw a tetrahedral in chemistry. Let's shorten this one a bit, and this one. Oh, that was a bit too short. Shorten it to about there, and there. That's lovely. Okay, that's how we draw a tetrahedral. So let's draw it again in this one. There. There. Okay, there. And we have to do exactly the same with the oxygen here. There, there. So all of these 3 are tetrahedra. Why are they tetrahedra? Well, because they have 4 electron directions. And when the electrons try and escape from each other around the sphere, the shape they make is going to be a tetrahedral. All right, and as you know, a tetrahedral has an internal bond angle of, let me have a cup of tea. an internal bond angle of 100 and what is 109. Let's draw that over here. Let's draw what a tetrahedral is. Why are these called tetrahedra? Oh, my computer keeps snapping to grid. Okay, this in the top right here is a tetrahedral. Okay, and when we say something is tetrahedral shaped, we mean inside, right buried in the middle, is the central atom, and the bonds go out to the vertices of a tetrahedral. That's what it means to be tetrahedral. All right. Okay, and within the tetrahedral, these bond angles within the tetrahedral are 109.5 degrees. All right, and this is what we mean by tetrahedra. Tetrahedra, which is the plural of tetrahedral. So carbon, nitrogen, oxygen all have 4 electron directions, and all form tetrahedra. That's the deal, I'm afraid. So let's put our other elements in, shall we? Now we've got to put our hydrogens in here. There. We've only got 3 hydrogens here, don't we? And we've only got, let's do a different color here, we've only got 2 hydrogens here. Okay, but they all form tetrahedra. So that's the important thing. Why do they form tetrahedra? Well, let's get a nice different color here. Let's get a nice silvery color. They form a tetrahedra because they have 4 electron directions. Now, it's not easily seen in ammonia or water, is it? But the other 2 electron directions are taken up with lone pairs. Okay, so there you go. That's the form of all of them, and they are all based on tetrahedral shape. Okay, so let's look at this. Well, the methane is easy, isn't it? This is just 109.5. They're all 109, and we'd say the HCH bond angle is 109.5 degrees. And this one is the true tetrahedra, or tetrahedral, isn't it? So methane is a tetrahedrally shaped molecule. Why? Because it has 4 electron directions. Simple as that. All right, let's have a look at this one. This is ammonia now. Well, this would be 109, wouldn't it? But this thing on the top, this thing here, is known as a lone pair. Okay, so there's nothing there, is there? There's no atom there. There's nothing at the top. Okay, but it still thinks it's a tetrahedral. But there's a lone pair on the top. Now, the lone pair squashes the molecule down because the lone pair has greater repulsive abilities. So this has greater repulsive abilities. Okay, and because it has greater repulsive abilities, it pushes these hydrogens down, these bonds down. So this would have been 109.5 if there was if this wasn't a lone pair, but there is a lone pair and it squashes it down a bit. So it squashes it down to about 107. Now, the shape of this thing is not a tetrahedral, is there? Because there's nothing at the top. So it's a tetrahedral without the top bit, and we call that a pyramidal shape because it's the shape of a pyramid. So we say ammonia is pyramidal. All right. Now, the lone pair on all nitrogens is really important. Lone pair on N and oxygen atoms must not be forgotten. Okay, and because of that, it's pyramidal. All right, so, and it has a bond angle of 107. So let's have a look at this one. Well, this one is a tetrahedral, but it's squashed and it's squashed again. So if it was a tetrahedral, it would be 109. If it had 1 lone pair, it would be 107, but it has 2 lone pairs. So it squashes it even more, and it squashes it to 104. I think 104.5. I think I can't remember. All right, so this one is based on a tetrahedral, but since there's nothing here and there's nothing here, all right, all we see is the 104. All right, it's kind of like an invisible tetrahedral that's been squashed a bit. Okay, now these things, the bond angle here, as you see, is 104, and we just call these bent or non-linear. All right, not a very interesting word, is it? But these are bent or non-linear, or the worst I've seen is they're V-shaped. Okay, so what makes them not tetrahedral is the lone pairs. Okay, and that's really important. You must never forget the lone pairs, all right, because they change the shape of the molecule. All right, so there's 3 types of 4 electron directions, and there they are. Okay, so let's move on to the 5 electron directions. This is 5 electron directions. Now, 5 electron directions is really beautiful, I think. And this is important. This PCl5, excuse me, PCl5 is the biggest example of this. This is the example. But in organic chemistry, we use this. It's an intermediate in an SN2 reaction. Okay, but I don't know if you know what that is yet, but we're going to use the PCl5. So if you looked at a PCl5 molecule, what would it look like? It would look like this. P1, 2, 3, 4, 5. Okay, and this is going to have 1, 2, 3, 4, 5. Oh, drawing electrons is painful. Oh, well, there you go. I think that's all done. But around the central, you can see 1, 2, 3, 4, 5. So it's got 5 electron directions. Now, this is probably the most complicated one to draw because you've got your P and you've got a Cl here. Oops, that's not right. You have a Cl here and a Cl here. All right, so this is the first part. Now this part of the molecule is planar because there's 3 electron directions. So this part of the molecule is actually trigonal planar, and the bond angles in this bit are 120. All right. Excuse me. Oh, I've got a cough. Now it's planar part, but obviously we have to put two more chlorines on, and these go up and down from the plane. Okay, and these two, now if you can imagine this is a plane. Okay, and within the plane it's trigonal planar, but then you've got one up and down perpendicular to the plane, and the angles here are 90 degrees between this one and this one. So this one has 2 types of bond angle. It's 90 and 120. So if you think there's a plane, and above and below the plane we have chlorines. So there's chlorine there, chlorine there, chlorine at the back, chlorine there, and a chlorine there. So within the plane here, the bond angles are 120, but up and down, the bond angles are 90. All right. Now, this is the one I always forget the name of. I think this is called trigonal, and that's for this part. And then you've got a pyramid at the top and a pyramid at the bottom. So this is known as trigonal bipyramidal. Is that how you spell it? Bipyramidal, something like that. Yeah. So this is called trigonal bipyramidal, and that's what you get when you have 5 electron directions. Trigonal bipyramidal. Ah, we're nearly there, everyone. Don't worry. Now let me have a 2-minute break and have a cup of coffee. Right. So, oh, you've been asking questions, and I haven't been watching. Her Wi-Fi is a problem. Okay, I can hear you, but I can't respond in time because my Wi-Fi keeps on lagging. Yeah, I know it's bad, isn't it? My Wi-Fi is awful as well. Do all trigonal planes have 100? Yes, they do. Natalie. Oh, my throat is killing me. Right, Natalie, what's 104.5? What does that mean? Type something, or Lebachang, you type something for her. Anyone know? What does 104.5 mean? Are you just telling me what the answer is, I guess? I don't know. I don't know what that was for. That was like 5 minutes ago. Are we all still here? Someone just type in something, just one letter, so I know you can hear me. Because with Wi-Fi problems, and maybe I'm talking and no one's there. Who knows? Is anyone there? No one's there. Well, that's depressing. All right, I've nearly finished anyway. Once I'm done the video, I was going to do questions. But oh, I see. Once I do the subject, I was gonna. Oh, that's right, it is. But Natalie. You're the one that asked for this. So do you understand? Have you learned anything? I know it's I've been quite fast, but have you got caught on with anything? Does it all make sense? Has anyone learned anything? I think our Wi-Fi is awful today, isn't it? For some reason. All right, not to worry. No one's answering, so I presume it's the Wi-Fi issue today. Anyway, we're nearly done. We're nearly done. So now I'm going to do the last one. Let's get rid of this, and I'm going to do the 6 electron directions. This is the last one. 6 electron directions. Okay. Now 6 electron directions. The example often given is sulfur hexafluoride. Sulfur hexafluoride. Okay, now obviously this has got 6. It's a sulfur with 6 fluorines around, isn't it? It's like this. So if you were to draw this, oh gosh, here we go. What colour solos? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. How, if you look around the central sulfur, oh, that's not good, but never mind, that will do. If you look around the central sulfur, it has 10. Oh, actually, it's got 12 electrons. It's got 12 electrons around the central sulfur. Okay, which in itself is quite interesting, but I'm not going to go into why it has. But if you look at the central sulfur, there's 12. 12 electrons. 12 electrons. But 12 electrons is equal to 6 pairs of electrons. And 6 pairs of electrons means 6 electron directions. And this is the prettiest shape, I think. So let's draw a sulfur, central sulfur. This is how I draw these. I draw a lovely rhombus around my central sulfur there. And then, oh, I don't want that actually. I want that. And then I draw my fluorines in. So there's 1, 2, 3, 4. And then I draw my bonds. There's a bond there. And this bit is supposed to show you it's planar. This particular part is planar. But now what we do is I get rid of these things because there's not really lines here. This is just to give you an idea of the planarness. Okay, so there's a planar bit, and up and down. Okay, you have a fluorine there and a fluorine there. Now this is interesting because there's a bond angle here is 90, and the bond angle between this and that is 90. And this shape is a square based pyramid. And it's 2 square-based pyramids, one on top of the other, and such a shape is known as an octahedral. Okay, now in AS, this is really the only example of an octahedral I can think of. All right, SF6. But in A2, this shape comes up big. Okay, this octahedral shape is much bigger. It's bigger. It's very important, bigger in A2 chemistry. It's not so big in this. It's only SF6 that I can think of. All right, but it's a beautiful shape, and it's how things bond in the A2. It's lovely. All right, and I don't know how good your maths is, but if you think of the 3 dimensions of space, the x-axis, the y-axis, and the z-axis, if you look, this thing shows that this one would be the z-axis. This is the y-axis, and this one would be the x-axis. So they bond in the 3 dimensions of space. All right, guys. Well, I've explained that. We've coming up to an hour now. I hope you understand it all. It's a shame we didn't get to the questions, but never mind. I took a bit longer than I would normally do in the theory part because I didn't manage to set up the recording straight away, did I? So, guys, well, have a nice day. Maybe next lesson, if you're interested, since there's only 3 of us, maybe, I don't know, maybe the lessons aren't as productive as I thought they might be. All right. So I don't know. Maybe we'll have a lesson on Friday. I don't know. But to be honest with you, we have to get a bit more interest, really, because it's a bit sad if only 3 show up, isn't it, really? All right. Let me finish this now then, and I'll post this onto the